Welcome back to Physics 12 into our foray into magnetism. So we've seen electricity the last 4 weeks or so, and that tied in nicely to gravity. So everything seems to be working together, and hopefully that's going to continue. So just a quick review of permanent magnets. So this is going to be a lot of information that you've known since you were probably quite a small child. And some of it will, obviously, a lot of it's going to be new when we get to electromagnetism. So we do know that magnets can attract and they can also repel. And we know the rules for that, which are like poles repel and opposite poles attract, right? So if you put a north and a south together, they're going to pull together. If you put a north and a north or a south and a south together, they're going to repel. So old news for us. And they're able to exert these forces because they are surrounded by magnetic field. So these are just like we've been talking about with our other fields like potential and electrostatic fields. They're just an area of influence. So if you put another magnet in that area or put other magnetizable materials in that area, then they can be affected by it. Now, because this is grade 12, because it's physics, we're not just going to leave it with some vague notion that uh, forces exist. We want to be able to quantify that. We want to be able to give a number to the idea of magnetic fields. So when we're trying to give a number to describe the quantities related to magnetism, we are going to refer to this quantity known as magnetic flux. And one way of looking at that is that it's the density of the field line. So when we were thinking of electrostatics, for example, if we drew a positive charge, we'd see the field lines pointing away from it, for example, and then where the field lines were closer together, that was a stronger field. Where those field lines were more spread out, that was a weaker field. So we have the same thing for magnetism. We just refer to it as magnetic flux. So it's the density of field lines, or you can say the number of field lines passing through an area. Now, this idea of passing through an area is something that we're going to see more in the coming weeks. So we're going to kind of define what that area is and why it's important when we talk about electromagnetic induction, which is going to be in about 5 weeks. So as we probably guessed, areas that have many lines closely together, these are going to be where we're going to have stronger magnetic fields. Okay, magnets have two poles. Now, we usually refer to them in short as the North Pole or South Pole, but what we really should be doing is, if we want to be a bit more specific, we should refer to these as the North Seeking Pole or the South Seeking Pole. And we'll see what that means when we talk about the Earth in just a moment. So when we're drawing field lines, just hopefully this is a review, we know that field lines are going to go in this general direction. So if you've ever seen a demo of this where, say for example, you put a piece of thin plastic over top of a magnet, and you sprinkle that with iron filings, you end up getting this pattern here, which you can see in this area here, this pattern here. Now, this is showing you where the field lines are. It doesn't necessarily show you the direction. So for example, if I told you this is north and this is south on the right, but if I told you this was south and this is north, would you be able to tell the difference? Not exactly. Not with a picture like this. Not with a picture of this iron filing. But just so you know, by convention, we do say that the field lines go from North Pole to South Pole. So it would look something like this and kind of going outwards in this pattern. As you know, not a fantastic artist, but nonetheless, that's sort of what we're looking at for that. So you notice that these look very similar to drawings that we did of dipoles. So remember when we had two opposite charges, for example, a positive and a negative charge, the field lines would look very excellent. Like switch these around. match it up with the magnet here. But when we were drawing field lines, we would draw them again going from positive to negative, and they would have this very similar shape that the magnetic field lines do as well. So they're going to be very, very similar to that. There is one difference, though, between dealing with magnets and dealing with charges, is there's no such thing as a magnetic monopole. So what that means is you can have a single positive charge sitting on its own. You can have a negative charge sitting on its own, but you can never have just a north pole sitting on its own. In fact, if you have a magnet, let's say this is my magnet here, and this is north and south. If I were to cut this in half, somehow I'm able to make a clean cut through that, but what I'm going to end up with is in fact two magnets that have a north and a south pole. And I can continue doing that down to a single atom, and that one iron atom will still have a north pole and a south pole on it. You cannot have just a north pole on its own or a south pole on its own. You discover one of those, and that's a guaranteed Nobel Prize for you. So, so far, we have never found a magnetic monopole, and as far as we know, they don't exist. Okay, so that is bar magnets. That's pretty much what you need to know about bar magnets. If you are curious about it, what bar magnet looks like is in a bar magnet, there are a bunch of what are called domains. So it's just these little areas. Now, on a magnet, these areas will be aligned. So if we zoom in here on these little areas here, each of these in a magnet would be more or less aligned, kind of in the same direction. So this would make the magnet magnetic, because overall all these regions have these small domains or these small areas which are all kind of gathered together in the same direction. So all these little areas here line up together. Now, in something that's not magnetic, or something that's, let's say we take a piece of iron, because not every piece of iron is going to be magnetic. All that means is that you're looking at the same similar setup, but some of the domains are basically they're all in different directions. So this might be this way, this way, this way, this way, etc. There's not really a set pattern. So if you take just a random piece of iron, you're probably going to get something like this, where they're not all lined up. It's not necessarily a magnet, but if you were to somehow align all these domains so that each little bit of iron or each little chunk of iron is all facing the same way, that's when you get a magnet. So that's how you can build a magnet as well. If you have a needle, for example, you have a long, thin, like a stitching needle, and then you rub a magnet against it, you can actually get these domains to all line up in the same direction, and you can turn that needle magnetic. Then you could use it for a compass, for example, float that on a cork or something in a bowl of water, and it will align itself with the North Pole. So you can make a magnet out of it. But if you also take a magnet and you bang it really hard a bunch of times, you also mix it up so it'll look more like this option on the right, where it's not magnetic at all. So you can make a magnet demagnetized by banging it, or you can make a non-magnetic piece of iron magnetic by aligning those different domains. Okay, so if we imagine the world as a gigantic magnet, what would that look like? Well, we know that if we have a north pole is attracted to a south pole. So if we were looking at the Earth, so here's my Earth here, and if I know that if I put a magnet here, the north pole is going to be attracted here, and the south pole is going to be attracted here. So what does that mean if we treat the Earth as a giant magnet itself? What does that mean for the Earth itself? Well, we know that north is attracted to south and south is attracted to north. So if we look at the Earth as a giant magnet, the geographical north pole of the Earth is actually the magnetic south pole of the Earth. So oddly enough, a north-seeking magnet goes to our geographic north pole, goes up to where Santa Claus lives, and the south pole goes down to where the emperor penguins live. But if the Earth was a giant magnet, then where the emperor penguins live, down in South America or down in Antarctica, that would actually be a magnetic pole. Okay, so I'm going to show a quick demo here about why the Earth is magnetic, and this is something that I would have shown you in class, but here we are. doing it live streaming. So if you want to take a look at this video, the link here just goes to this link here. So if you're on OneNote, you can click here. Otherwise, you can click on your sheet if you've opened it up. Okay, so here's a quick video.
I have a wire that goes through a piece of cardboard here, and I've got it surrounded by little tiny compasses. They're all pointing generally this direction. And I'm going to run current through the wire that will be coming up the wire this way from underneath. So based on the right-hand rule, there should be a magnetic field around this wire. In which direction? Let's find out. So I'm going to clip this on now. So it looks like all of the arrows are tending to go around in a counterclockwise fashion from this perspective. I'll turn the current back off. Now I'm going to reverse the current and run it the other direction. So in this case, the current will be flowing down the wire through the cardboard. And let's see what direction the field is there. And now they all seem to be pointing in a clockwise fashion around the wire.
Okay, so what we saw there is a piece of wire carrying a current created its own magnetic field. And so if you're wondering why is the Earth magnetic in the first place, and essentially as the Earth rotates, there is going to be moving iron core. There's lots of nickel in the Earth as well, and that's moving, and so those moving charges, those moving currents, essentially create their own magnetic fields. And if we want to know the direction of it, that video leads us to our first right-hand curl rule. So the first right-hand curl rule is what's shown in this picture here with the thumb and with the wire. So if we want to know the direction of the magnetic field, what we do is we would wrap our hand around the wire and we would point our thumb in the direction the current was flowing. So when he showed that in that first clip where he had the wire coming out of the page, so if you're looking at the screen, that wire was kind of coming towards you a little bit. And as the wire is coming towards you, if you point your thumb towards yourself as well, or point your thumb coming out of the page, that's going to be the direction of the current. And your fingers that are wrapped around the wire, those are going to show the direction of the magnetic field. So you'll notice when the current was coming out of the page, if you were to put your hand there with your thumb pointing up out of the page, and you curl your fingers, you'll notice that the compasses were all pointing counterclockwise. And then he turned the current around so it was going into the page. And as you point your thumb down into the page, if you look at the direction of your fingers, well, they're going clockwise. And so that is the first right-hand rule for current in a wire. So the thumb, your thumb is going to be, that thumb is going to be the direction of current, and fingers are the direction of the magnetic field. By the way, just a quick note, if you are writing the magnetic field, this is often just shorthanded to the B field. So B is our letter that we use in formulas for magnetic field. So the B field is going to be magnetic field, and then we would usually refer to the electric field as just the E field. Because when we get into the next few units, we're going to be mixing back and forth. So instead of writing them out every time, magnetic field, electric field, we can just refer to it as B or E. Okay, I'm going to show one more video. So what we've seen so far, and this is the link right here, what we've seen so far is that current, and if we think about that for a moment, a current is just moving charge. So a current, there's a little baby bird that landed right on my window. That's adorable. Okay. So there is a current is able to create a magnetic field, and now we're going to see what the effect is of a magnetic field on the current. that again. So essentially what just happened there is when they turned the current on, so there's current flowing through the wire, and there's a magnetic field that is surrounding this piece of wire here. So what we're seeing is the magnetic field is having an influence on the wire. So we know a wire creates its own magnetic field. However, when a magnetic field is in place there, the magnetic field created by the wire, as well as the magnetic field created by this permanent magnet that's sitting there, those two things are going to have an interaction with each other. And so we know that a magnetic field can have an effect on either a current carrying wire, or what we're going to see next week is that it can have an effect on even individually charged particles. Because what is a current if it's not just simply a flow of these charged particles moving down a wire? And so by the force going upwards on the wire, and when you turn the other way, now it'll apply a downward flow on the wire. Okay, so when we have a current carrying wire placed into a magnetic field, it is going to feel a force, as we saw in that video. Now the force acts perpendicular to the magnetic field, and it also acts perpendicular to the wire, or to the current in the wire, which obviously are going to have the same direction. So if we think about what this is saying is, if we look at it, let's say we look at that experiment from the top. So from the top, there were these two magnets here. I'm going to call this North Pole, and I'm going to call this South Pole. And so if we look at these two magnetic poles, there's a magnetic field that's going this way between these two. We know it goes from north to south. So this is the magnetic field here, and sorry, magnetic field, it is a vector, so it gets a vector symbol. We know that there was this wire, and let's say the wire was moving this direction, and this was the direction of our current, and we know current is the letter I. And what direction was the force? Well, when we're viewing this from the top, the magnetic field, in this case here, it didn't really show in the video which is north and south, but I can let you know, in this case here, this would have been the example where the force was into the page. So we're going to see that in a second here. This is the first time that we're seeing a challenge where we're not really able to draw arrows, because it's not, we essentially for these problems have to think about this in 3D. So this is going to give us a new challenge. And so what I wanted to write down here is that when we want to show something into the page, meaning, so if I was to drop my pen on this page here, pointing directly downwards, that's into the page. This is drawn by this symbol here. So into the page is this symbol here, and out of the page, this is drawn by this symbol here. Now, how I was told to remember that when I was a youngster learning physics just like you is think of an arrow. So if I were to fire an arrow, so I'm going to bow an arrow, I'm firing that arrow away from me. Well, as the arrow is flying away from me, what I'm going to see on the arrow are the tail feathers. So when you have an arrow like this, moving in this direction here, when you look at it from the back, terrible artist, I know. When you look at it from the back, what you're going to view is the tail feathers as it's moving away from you. So that's these parts here, and that's going to look like an X as it's flying away from you. As an arrow is flying towards you, all you're going to see is the tip of this arrow. It's going to look like a point. So that's how you can remember the symbol. So in this particular case here, if we have the magnetic field going from right to left, the current going downwards, we are going to see the force in this case acting downwards on it. So I'm going to write that. So the force is going to be downwards. So you'll notice that downwards or upwards would be the only two possible directions that would be both perpendicular to the current and perpendicular to the magnetic field. And in fact, you'll notice that all three of these are going to be perpendicular. So the magnetic field will be perpendicular to force and current. Current will be perpendicular to force and magnetic field, and force will be perpendicular to magnetic field and current. So what factors do you think might affect the magnitude of this force? So pause the video for a second, have a think about that. What factors do you think might make that force larger or smaller? So picture that video again. What factors do you think would make that a stronger force or a weaker force? Okay, if you've had some time to think about it, hopefully you've come up with the following three things. So you can see that they used a big 12-volt battery. Well, that's probably because they wanted to have a larger current. So that is going to be one of the factors. It's going to be the I, which is the symbol for current. Now they used also some pretty powerful looking magnets there. So you might have guessed that the magnetic field is also going to be one of the factors that affects that. And another one that's going to be a bit more difficult to guess is going to be L, which is the symbol for the length of the wire. So what we really mean by the length of the wire, what we really mean is the length of the wire that's in the B field. So the longer the piece of wire is that's within the area of the magnetic field, the more force there's going to be. And in fact, that's going to be our formula here. So the formula is F equals Bill. So F equals BIL, magnetic field multiplied by the current and multiplied by the length of the wire. And in terms of the angle, what effect is the angle going to have? Well, the effect of the angle between the magnetic field and the current. So if we look at this red line going here for the current and this blue line going here for the magnetic field, the force is going to be greatest when those are 90 degrees to each other. So 90 degrees apart, or perpendicular we can call it. And the force is going to be 0 when the angle between the magnetic field and the current equals 0 degrees, or when they are parallel. And so if we want to, we can actually modify this formula here, the one that we have for the magnetic force on a current carrying wire, and it should be F equals Bill times sine theta. So I'm not going to, I don't think that I'll really be asking you test questions about BIL sine theta, but it is good to know. Okay, so that is how we can tell what the actual force is going to be. So we know it's going to be strongest when the current and magnetic field are perpendicular like they are in this drawing, and it'll be 0 if those two things were parallel. And oh yeah, I already mentioned this before. So out of the page and into the page is this symbol here, out of the page is this symbol here. So the arrow is flying away from me and I'm looking at the tail feathers, and the arrow is flying towards me and I'm looking at the point. Okay, so going back to, we talked about magnetic flux, and magnetic flux is sort of the overall number of field lines that pass through an area. But if we want to know how densely packed those are, then we use a quantity called flux density. And in fact, flux density is the one that has this magnetic field symbol B. So this is the one that is the actual B that we're referring to. So how densely packed those field lines are, or essentially how strong the magnetic field is. And this is named after one of the coolest scientists of all time. Hopefully you know the answer to that. The coolest scientist time is Nikola Tesla. If you want to know why he's so cool, I suggest Googling it. The unit for flux density is the Tesla. Notice it's lowercase because it's a unit, not a human being, but the symbol is going to be a capital T. And 1 Tesla as a unit is going to be 1 Newton per meter per amp, or just written this way, 1 Newton per meter per amp. So essentially what it is, it's the flux density that's required if you wanted to exert a 1 Newton force on a 1 meter wire carrying 1 amp of current. So 1 Newton of force for every meter of wire, for every amp that's flowing through it, that is what a Tesla is. Yeah, and 1 Tesla is actually quite a large force. It's quite a very strong magnetic flux density. So if we're near a small bar magnet, that's probably about 0.01 Teslas. Some of the strongest electromagnets in the world are only about 10 Teslas. And inside a sunspot, very magnetic, is about 0.15. Surface of a neutron star, though, those are very magnetic. Those are around 100,000 Teslas, which is just unbelievably strong. Anything that's even remotely magnetic would just, yeah, it would be pulled towards the surface of a neutron star with a force that's hard to comprehend. Okay, so how do we determine the directions? And this is where we come to our second or third right-hand rule. This is often referred to as the third right-hand rule. So we've kind of skipped the second one today. We'll do the second one next week. But the third right-hand rule is a different symbol that you have with your hands. So I've changed this slightly. So if you look at this picture here, we've got your thumb representing the force, your current represented by your index finger, and your magnetic field represented by your middle finger. Now what I personally like to do is I like to take my ring finger and my pinky finger and also aim them the same way. And the reason why I do this, it reminds me that they're field lines. Because if you line them all up together next to each other, they look like 3 lines. So that tells me, oh yeah, these are the field lines for my magnetic field. Current is easy to remember because it's pointing the direction. When you point at something, you're basically saying the direction something is moving in. And so this is telling you the direction of the motion of these positive charges in a wire, or as we get to individual particles, it'll be the same thing. This is the direction that a positive charge moves. So the right-hand rule, again, just to summarize, the force is your thumb. The current is your pointer finger or index finger. And your field lines are going to be the other 3. So that's going to be your middle, ring finger, and pinky finger. Those are the 3 ones there. And so what I've done is, normally I'd be showing you just showing my the hand demonstrations in class, but I can't really do that. And so what I've done is I've made some pictures of my hands in all these different variations. So let's give this a try for example 1. So what I would love for you to try doing, it does take some practice with these. So I would really appreciate if you pause the video, try doing the calculation, and then try figuring out the direction based on your fingers here. So in this case here, before you pause the video, it's a magnetic field of 120 milliteslas. Keep in mind the unit there. The wire is at 90 degrees to the field lines, and the field lines are due north. So I'm going to draw the field lines in green, and these are going to be due north. So this is my B direction here, due north. And the wire is going from east to west. So the current is going from the east to the west, so that's going to be in this direction here. That is my I. And so if I've got a magnetic field going north, that's my 3 other fingers, my index finger, or sorry, my pointer finger, my index finger, that's showing the direction of the current, and that's going from the east to the west. So what is going to be the magnitude of the force? First of all, calculate that. And also, I want you to figure out the direction. So how can you keep your hands? And the secret to this is that you can change the orientation of your hand, but you can't change the shape of your hand. So you have to have all of these at 90 degrees. So you'll notice if you look at any of these pictures here, my thumb is pointing in this one to the right, my 3 fingers are pointing up, so those are perpendicular, and my index finger is pointing into the page, and so all 3 of those are perpendicular. So the rule is you cannot change the shape of your hand. All you can do is rotate your hand to try and get these 3 things to line up. So try it for yourself, pause the video, try doing the calculation, and then try figuring out the direction as well. Okay, so if you are back and you've tried this question out yourself, well, first of all, let's figure out what the force is going to be. So the calculation itself, not too bad. F equals Bill, and we've got 120 times 10 to the minus 3 Teslas, it's milliteslas, multiplied by the current of 14 amps. And we're going to multiply that by the length, which is 5.0 meters. And so let's see what we get here. We have 120 times 10 to the minus 3 multiplied by 14 and multiplied by 5. And that gives us a value of 8.4. Okay, so the answer is 8.4 newtons. But what direction is it? So the one way of solving these, if you want to just do them by trial and error, is pick one of these options here. So what I mean by that is pick either B or I and try and find something. Try and find the options that you have that line up for it. So let's say I want to turn my 3 fingers for B. Let's say I want to point these to the north, not into the page or out of the page, but just straight north. So that could be this first picture here. My 3 fingers are pointing up north. That could be this one here if I rotate this picture 90 degrees to the left. So now my 3 fingers are pointing upwards. This picture here, the fingers are pointing into the page. This one here, let's rotate it twice again. And now the 3 fingers are pointing up or north in this case. So what I'm drawing this as north, south, east, and west. And lastly, I've got this one here, which I'm going to rotate 90 degrees. Okay, so these 4, 1, 2, 3, 4, these are all the ones where my 3 fingers representing the field are pointing north in this example here. So I've got these 4. Now, hold your hand in these 4 positions here. So you can point your fingers, point your index finger away from you. We'll start with number 1. And if I rotate my wrist to the left, I'm going to get this finger here. So my index finger was pointing away from me over here. I'm turning my hand to the left. Now it's pointing this way. If I turn it left again, kind of awkward position, but now I'm pointing towards myself. And if I turn it right again, a very awkward position, but now I'm pointing my finger to the right. So one of these 4 is going to not only match up with my 3 fingers pointing to the north, but it's also going to match up with my current pointing to the west. So this one here, the first one, the current is pointing away from me, not to the west, but away from me. This one down here, the current is pointing towards me, again, not to the west. This one, the current is pointing to the east. And this is the only one here where the current is pointing to the west. So this is the one that matches these 2 quantities. In this case here, the field lines are pointing north and the current is pointing west. And so what direction is my thumb pointing? Well, my thumb is pointing, as you can see in the picture, it's pointing into the page. And so if I want to know the direction of the force, well, the force is going to be 8.4 newtons, and it's going to be into the page. Okay, now if this makes sense for you, because some people pick up on this right away, and some people need a bit of practice. So if this makes sense to you, please feel free to try and solve the following questions on your own. And you can stop the video right here, and that's fine. There's nothing else for me to share with you. If you're still finding this difficult, then I'm going to try working through these 4 problems with you. But I know that this video is already getting a bit long, 35 minutes. So if you feel confident, then please, by all means, stop the video here. And if you do want a bit more practice, then by all means, stick around. So in these 4 questions here, this is question A, and B, and C, and D. So for question A, we've got the magnetic field's given, the current is given, and we're trying to find the force. And what I want you to do, I'm not going to go through the numbers, I'm just going to go through the direction that we're going to get. So what we have here is the magnetic field pointing vertically down. So that means my 3 fingers need to be down, and by down, I really always mean into the page. So the 3 fingers pointing into the page, that just leaves me with this picture here. This is the only one where the 3 fingers point into the page. All of these, the 3 fingers are pointing north, as we saw, and this one, they're coming out of the page. So what I have here, let's move this picture down here. I've got 3 fingers pointing into the page. And I've also got my my current, which is my index finger, pointing north. So what do I have to do with my hand? Well, I need to turn it around. So my three fingers are still going to be pointing into the page, but I need to turn my index finger so it points north. So to do that, I need to rotate this twice. And so if I rotate my hand twice, you'll see here I've got my three fingers still pointing into the page. My index finger, which is the current, is pointing north, and my thumb is telling me the force. So in this occasion here, what direction is the force? Well, the force, if the index finger is pointing north, then the force is going to be to the west. And I'll leave it to you to find the numbers. Question B. Again, we've got our three fingers pointing vertically down. That makes our life easier. So I know it's going to be one of these variations here. And I've got my force pointing south. Well, the force is my thumb. So what I need to do to this picture is I need to make my fingers, keep my fingers where they are. So I'm just going to rotate this picture around the finger axis here. But I need to make sure my thumb is pointing south. So I need to rotate this left by 90 degrees. And now you'll notice that the fingers are into the page vertically down for my B field. My force is pointing south with my thumb, and the current is being pointed out by my index finger. And so this is also going to be west. And one last, I'll leave the fourth one to you. And the other questions below also have practice in there for the direction. But let's try this one here. My current is pointing due north. So what that leaves me with is my index finger pointing north. That leaves me with this picture here. This picture, I could rotate it by 90 degrees so the index finger would point north. And this one here and this one here. Let's rotate this one to the left. And let's rotate this one to the right. And now in these four examples, let's rotate this one as well. In these four examples, my current is pointing north. So that's this one, this one, this one, and this one. In all four cases, my index finger is pointing north, and the other two, it's coming out of the page. Okay, so that leaves us with four options for this one here. And in this case here, it's saying that my force is west. So there's only one of these four where my force, or my thumb, is pointing to the west, or pointing left on the page here. And that's this one here. And so now we've got two out of those three things nailed down. My current, which is my index finger, is going north, and my thumb, which is my force, is going west. And so what direction is the direction on the magnetic field? Well, the magnetic field is indicated by my fingers. And so what direction are my three fingers pointing? Well, the direction that they're pointing is into the page. So that is my answer for part C. Okay, if you have more questions, there's always FitBlock on Wednesdays, or feel free to email me before that. I'm happy to answer your questions for you. And hopefully you found this week educational and somewhat interesting. Thank you.